Welcome to Lecture 13, Limits, Section 3.7 of the text, Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert Eyabi. In the previous sections of Chapter 3, we studied various properties of continuous functions. So we now turn to the study of the behavior of functions near points that are not necessarily in the domain of the given function. So for a set D of numbers, D is a subset of the set of real numbers, and a point x naught, we use the notation D backslash the singleton x naught to denote the set of all values x in D such that x is different from x naught. It is convenient to say that a sequence xn is distinct from the point x0 if xn is different from x0 for every index n. We would also represent the set D backslash the singleton x0 as D minus the singleton x0 or D intersection the complement of the singleton x0. So let's go ahead and start with a definition. Subsection 3.7.1 definition. For a set D of real numbers, the number x0 is called a limit point of D provided that there is a sequence of points in D backslash the singleton x0 that converges to x0. So there is a sequence of points in D. X0 is not one of those sequences such that the sequence would converge to x0. Example, let D be the open interval AB, A less than B. Then D is a subset of the set of real numbers. A and B are not elements of D, but we claim that A and B are limit points of D, i.e., we can find sequences A and Bn such that An converges to A and Bn converges to B, and those sequences would have to be sequences in D. Okay, so that is what we mean when we say x0 is a limit point of the set D. So let's go ahead and verify that A is a limit point of D. Define the sequence an as an equals a plus b minus a divided by 2n. Observe that if n equals 1, then we have a plus b minus a over 2, which would just be a plus b divided by 2, and that is the midpoint of AB. So the sequence an is a sequence in D. An converges to A, which is not a point in D. So A is a limit point of our set D. Similarly, we can verify that B is a limit point of our set D by defining a sequence Bn that converges to B. But the Bn must be a sequence in D. So I would leave that as a simple exercise for serious students. Construct for me a sequence Bn that is clearly in D and converges to B, which is not a point in D, confirming that B is a limit point of our set D. Now, recall that a set of rational numbers and a set of irrational numbers are both dense in R. In other words, if I pick any point in R, there is always a sequence in Q and a sequence in QC that will converge to that point. So every real number is a limit point of Q, and similarly, every real number is a limit point of QC, the set of irrational numbers. Subsection 3.7.2 definition. Given the function f from a domain D to the set of real numbers R, and a limit point x0 of its domain D, for the number L, we write limit as x approaches x0 f of x equals L. That is, write the limit of f of x as x approaches x0 with x in D equals L. This holds provided that whenever the sequence xn in D slash the point x0 converges to x0, then we have that limit as x approaches x0 of f of x equals L. Let's look at a couple of examples. Example 1. Find the limit as x approaches 2 of the function f of x. In other words, as x approaches 2, f of x becomes what? That is the question. So if we can substitute 2 for x in f of x and get a real number, then that would be our answer. But if for some reason either the denominator vanishes or we end up with something that is not a real number, then we have more work to do. So for this first example, as x approaches 2, we look for f of 2, and that gives us square root of 9 over 4, which is 3 over 2, and that is a beautiful real number. So we stop right there. We can say that the limit as x approaches 2 of this function is 3 divided by 2. As easy as that. The next example, though, would require us to apply the power rule, or the difference of powers formula as we call it. Example 2. Find the limit as x approaches 1 of the function x squared minus 1 divided by x minus 1. So we attempt to substitute 1 for x in f of x and quickly realize that the denominator vanishes. So there is a problem. But what do? Algebra. Difference of powers formula. X squared minus 1 is the same as x plus 1, x minus 1. So we substitute this for x squared minus 1 and cancel off x minus 1, x minus 1. We're left with x plus 1. Direct substitution using the sum limit theorem gives us 2. So we can say that the limit as x approaches 1 of the function x squared minus 1 divided by x minus 1 is 2. And we're done. It gets even more exciting. Example 3. Find the limit as x approaches 8 of the function x minus 8 divided by x raised to the power 1/3 minus 2. Again, if we substitute 8 for x, we end up with a denominator that vanishes. We use algebra once more. And recall the difference of powers formula. We use a cubed minus b cubed, which is a minus b times a squared plus ab plus b squared. And if we solve for a minus b, that gives us a cubed minus b cubed divided by a squared plus ab plus b squared. We've done this before several times. X to the 1/3 is our a. 2 is our b. So a minus b would be x to the 1/3 cubed minus b is 2. So that would be b cubed. And the denominator would be x to the 1/3 squared plus 2 times x to the 1/3 plus 2 squared. We are simply using this equation up here, knowing that a is x to the 1/3 and b is 2. And that simplifies to x minus 8 divided by x to the 2/3 plus 2x to the 1/3 plus 4. So we go ahead and substitute our newly found expression of x to the 1/3 minus 2 into our limit, and that gives us limit as x approaches 8 of x minus 8 divided by x to the 1/3 minus 2 being equal to limit as x approaches 8 x minus 8 divided by our newly found expression for x to the 1/3 minus 2. And very clearly you can see here that x minus 8 and x minus 8 would cancel out, and we're left with x to the 2/3 plus 2x to the 1/3 plus 4. As x approaches 8, that leads to 4 plus 4 plus 4 equals 12, and that is our answer. Very important. Difference of powers formula. We're going to use it one more time. Let k be a natural number. Prove that the limit as x approaches 1 of x to the k minus 1 divided by x minus 1 equals k. Again, if I attempt at substituting 1 for x, the denominator vanishes. Difference of powers rule. X to the k minus 1 factorizes out as x minus 1 times x to the k plus 1 plus x to the k minus 2 plus x cubed plus x squared plus x plus 1. And observe that we have k terms right here. So if we go ahead and substitute our newly found expression for x to the k minus 1 back into our limit problem, then we end up with limit as x approaches 1 of x to the k minus 1 divided by x minus 1, which is limit as x approaches 1 of x minus 1 times x to the k minus 1 plus x plus 1 divided by x minus 1. Now I can cancel out x minus 1 and x minus 1, and I'm left with k terms. And substituting x equals 1 for each of these would end up with 1 plus 1 plus 1 k times, and that gives us k. So we can conclude that the limit as x approaches 1 of x to the k minus 1 divided by x minus 1 is k. Okay, we would put a pause at examples 4 now and go ahead and look at a few theorems from section 3.7. Subsection 3.7.3 theorem. Let f and g be functions. Both functions have domain D and their codomains R. Let x naught be a point of their domains. Suppose that the limit as x approaches x naught of f of x is a, and the limit as x approaches x naught of g of x is b. Then we say that the limit as x approaches x naught of f of x plus g of x would simply be a plus b. The limit as x approaches x naught of f of x times, not composition, times g of x is a times b. And if b is different from 0, g of x is different from 0 for every x in D, then we can say that the limit as x approaches x naught of f of x divided by g of x is a divided by b. Call the first equation plus, call the second plus plus, and call the third plus plus plus. So let's go ahead and look at the proofs of these three statements from Theorem 3.7.3. Proof. Let x naught be a sequence in D slash the singleton x naught that converges to x naught. From the definition of limit, it follows that the limit as n approaches infinity of f of xn is a, and the limit as n approaches infinity of g of xn is b. We are given that the limit as x approaches x naught of f of x is a, and the limit as x approaches x naught of g of x is b. So 1. From the sum property of convergent sequences, that implies the limit as n approaches infinity of f of xn plus g of xn equals a plus b. Again, we are using our conclusion here that what we have up there implies that the limit as n approaches infinity of f of xn is a, the limit as n approaches infinity of g of xn is b. So by the sum limit theorem, we have limit as n approaches infinity of f of xn plus limit as n approaches infinity of g of xn, and that would simply be a plus b. Call that equation 1. Similarly, following the product limit theorem, limit as n approaches infinity of f of xn times g of xn is a times b. And thirdly, if g of x is different from 0 for every x in D and b is also different from 0, then by the quotient limit theorem or the quotient property, limit as n approaches infinity of f of xn divided by g of xn is a divided by b, and call that equation 3. So you can change this to 3. So we have the first one, 1, 2, and this should be 3. From the definition of limit, plus follow from 1 to 3, and therefore we can conclude that the equations plus and plus hold. Therefore, Theorem 3.7.3 is proved, and we are done. Okay, so recall, change the 2 to 3. Of course, it is expected that once we have the sum, the product, the quotient, our next thing to think about would be composition, since we are dealing with functions. So let f be a function from D to R and g a function from U to R. Suppose that x naught is a limit point of D such that the limit as x approaches x naught of f of x equals y naught. Call that equation star. And y naught is a limit point of U, x naught limit point of D, y naught a limit point of U, such that limit as y approaches y naught of g of y equals L. Call that equation star star. Moreover, Suppose the image of f on the set D slash the singleton x naught is contained in U slash the singleton y naught. Call that star, 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 3 stars. Then we can say that the limit as x approaches x naught of G composed with f of x is L. Right here, that is the same L. We started off with x approaching x naught, giving us y naught, y approaching y naught, G of y, giving us L, and we claim that the composition G composed with f of x would converge to L as x approaches x naught. Let's go ahead and prove that. Proof. Let xn be a limit in D slash the singleton x naught that converges to x naught. From star, right here, it follows that f of xn converges to y naught. Assumption star, star, star. This is the assumption star, star, star. F of D slash the singleton x naught is contained in U slash the singleton y naught. So f of D slash x naught is contained in U. That is what permits us to define the composition G composed with f. Assumption star, star, star implies that yn is a sequence in U slash the singleton y naught. So from double star, it follows that G of yn converges to L. And this is double star. G of yn converges to L. So putting everything together, the limit as n approaches infinity of G composed with f of xn equals L. And as we concluded in Theorem 3.7.3, that simply means the limit as x approaches x naught of G composed with f of x equals L, and that concludes the proof of Theorem 3.7.4. Before we conclude section 3.7, let's have a little discussion to see the power of the composition property through what I call an example. Suppose f is a function from the set of real numbers to the set of real numbers and has the property that the limit as x approaches 0 of f of x minus f of 0 divided by x equals L. There are a couple of conclusions we can draw following the composition property. Number one, it follows that if k is a natural number, then the limit as x approaches 0 of f of x raised to the power k minus f of 0 divided by x raised to the power k is also going to be L. That is interesting. Moreover, for every alpha in R, alpha different from 0, the composition property also implies that the limit as x approaches 0 of f of alpha x minus f of 0 divided by alpha x equals L. So you can see that as long as what you have here equals what we have down here, see what we have, see what we have, see what we have, alpha x, the limit is still L. And also there is this interesting problem. The limit as x approaches 0 divided by x. Observe that we have alpha x here, and here we do not have alpha x, we only have x. So what do? Well, very easy. Multiply and divide by alpha. Alpha is different from 0. So I can transform my x to alpha x, but I have to make sure I multiply the numerator by alpha also. And by the constant multiple limit theorem, my alpha comes behind the limit sign, and this limit now becomes limit as x approaches 0 of f of alpha x minus f of 0 divided by alpha x, and all of this equals L times my alpha, and that will be alpha L. So if I can conclude that the limit as x approaches x naught of f of x minus f of 0 divided by x equals L, there are so many conclusions I can arrive at immediately just from this knowledge. That brings us to the end of section 3.7, lecture 13, and I look forward to seeing you in lecture 14, which would be the start of chapter 4. Thank you and God bless you. Bye bye.